So we consider inverse scale law. There are many forces we experience in everyday life, and mostly they are contact force. If you walk, if you ride, in any case, the most important phenomenological force is friction. Without friction, we cannot accelerate or we cannot decelerate. If we cannot decelerate, we can make many collisions. However, in nature, there are two fundamental forces that makes action at a distance. Action at a distance means it never touch, however, it brings in any motion. For example, a magnet, it applies some force to a metal. Gravitation, it pulls, the sun pulls the earth, and we are rolling around the sun. In addition, any atom traps electrons. Okay? Nucleus has many protons, it has a positive charge, and electrons are negatively charged. The electrons are trapped to nucleus that makes atoms. So these two fundamental forces are absolutely different, but their mathematical nature is absolutely the same. Very strange. In addition, the gravitational force is attractive only. Two masses attract each other, only attract. However, any two charges attracts if the two charges are of different opposite sign. Sometimes they are of this equal or the same kind of charge, positive, positive. Then the force are repulsive. As you already learned in physics 1, any two forces communicated by two objects must be the same in magnitude. However, their sum is always zero. That means they are mutually additive inverse. One force applied to particle 2, another force applied by second particle to the first particle, this is a zero. Zero vector. Sum is a zero. That means one thing is an additive inverse of the other. So equal magnitude, but opposite direction. In any case, the magnitude decays proportional to 1 over r squared. If you bring this 4 pi together, what you find is the denominator factor contains the area of a sphere of a radius r, 4 pi r squared. So strength of this action at distance force decays inversely proportional to the area of a sphere. Very interesting. That is the origin of Gauss' law. When we consider this action at distance, that is inverse scale law, not restricted to the inverse scale law, any conservative force, we have to take the derivative to find the force from the potential energy. And actually, to find the potential energy, you have to integrate the work by making use of a force. Force integrated over path and attach negative sign, then you will find the potential energy. If the potential energy is defined, then we say this force is conservative. Why? We know force integrated over path is according to the work kinetic energy theorem by Coriolis. It is the change in the kinetic energy. And usually you write 1/2 mv squared, something like that. And because it's a negative sign, this is a positive sign. They are the same. Sum is a 0. Then means sum of potential energy and kinetic energy, that's the difference is 0 always. Therefore, we define this by the total mechanical energy, and total mechanical energy is conserved if a force is conservative. If a force is conservative, this integral is uniquely defined, and this integral is independent of the path connecting the initial and final point. That's the fact for the conservative force. If you want to extend this idea to apply this idea to understand the nature of inverse scale law, we begin with the two-dimensional case first. Let us first consider the radius on the plane, xy plane. Bring me a point, origin. We assume the force origin is fixed at the origin, like the sun, which is very heavy in comparison with the mass of the earth. Then this force center is always fixed in a simple approximation, and the radius represents the distance between the two particles. They can be massive particles sharing the gravitational force or charged particles, the distance. In case this motion appears on the two-dimensional plane, my radius is just square root of x squared plus y squared. And we assume that there exists a function f of r. R is this, and we would like to compute the partial derivative with respect to x and y. Partial derivative, we denote this one by round instead of d, that is for the normal derivative for a single variable function. In here, our r is a function of x and is a function of y simultaneously. Therefore, partial derivative takes care of a single variable change, and the other or many other, the other variables are fixed. Therefore, we call this is a partial derivative of f with respect to x. We can also define the partial derivative of f with respect to y. In that case, I keep these x value invariant and vary y only. That's it. Next, to speed up the calculation, it is very clever to find a way to simplify the calculation in a systematic way. The reason is that this function is a pure single-valued function of R. Therefore, we make use of R as a mediator. The variation of x lead to the variation of R. Therefore, we first take the derivative with respect to R, and then the variation of R is divided by the variation of x. This notation is quite useful, which is developed by Leibniz instead of Newton. Newton used primes. So it is a very inconvenient. In some cases, it is convenient, but in this chain rule application, Leibniz rule is much, much better than Newton's way. Okay, in a similar manner, y partial derivative can also be obtained by taking the r derivative first and take the r derivative with respect to y. In here, the derivative of f with respect to r is nothing but the normal derivative because this is a function of a single variable r. Okay, we are ready to attack the problem. Oh, there is a typo. We have, instead of 2, it should be x, you know. So derivative of square root is 1 over 2 square root of 2, square root of x. And therefore, as a partial derivative, we use this expression in here. And again, we use the chain rule. This guy derivative is 2 times this, and this guy, we take the derivative with respect to x. Therefore, this one is common, that is 1 over 2r in the denominator, and this one becomes 2x. So 2 cancels to find x over y. In a similar manner, r's partial derivative with respect to y is y over r. As a result, what we are interested in this f's derivative. Okay, f's x derivative is f's r derivative, and then r's x derivative. And we copy this result. This is x over r, and this is y over r. And we identify this one. F's r partial derivative is actually the total derivative. There is no difference at all. So we are ready to attack the problem for the inverse square law using these formulas. This is the most general case for the inverse square law. We are actually living in the three-dimensional Euclidean space. And these, or E1 hat, E2 hat, E3 hat, are unit basis vectors along the x, y, and z axis. So this one, I denote this by x1, x2, x3, and this is unit vector hat E1 and E2 hat, and this is E3 hat. Okay. All right. Now, using Pythagoras' theorem twice, the distance between these 2 points, origin and point x, is this. You can apply the Pythagoras theorem twice, then you will find this projection. And for example, this is x1 and x2. Then what's the diagonal? This is x1 squared, x2 squared. And then this is another right angle, this right triangle with and x3. So hypotenuse is a square root x1 squared, x2 squared plus x3 squared. Okay, this is the radius. We are ready to attack the problem. The force is given like that. So this question asks us, what are the dimensions of the constant? Sometimes you might ask why I use the plural instead of singular. The reason is that whether it has a single power or not, we have a collection of powers, something, something, something. So this multiple information is necessary to find the complete dimensions. It is not a single dimension. Even though it is a 0, 0, 0, it has the three kinds of information. So I usually use the plural here. Force is mass times acceleration, and mass is the dimension. Acceleration is double time derivative. The double time derivative is time appears twice in the denominator and length appears in the numerator, single time and double time, so minus 2. Okay, that's dimensions of force. And what is the dimensions of a constant K? We remember the Coulomb's law, it used to be 1 over 4 pi epsilon 0, and gravitational force Gmm. Sure, that there is a Q1, Q2 multiplied. So these are two complicated objects, and actually they are of the same dimensions. Okay, so this K can be inferred from the fact that this guy is a unit. Unit means it is absolutely one. That means no physical dimensions in it. The only physical dimensions are contained in R. So move this one to the left-hand side, you find force multiplied the radius squared, and I copy these results in here and divide this multiply length squared. So this power has been increased from 1 to 3. Next, we compute the gradient. Gradient is represent the slope. And if there is a mountain, there's a contour. Contour shows the line connecting the same altitude. Same altitude. That means that there is no height difference at all. Gradient is the direction to which the height increases maximally. Okay? In physics, there's a potential energy, then the direction of a force is minus gradient of potential. Why? This is a potential. Well, then if you roll a ball, it moves around here. Always particle wants to move from higher potential to lower potential. So negative gradient means gradient is along this direction. However, negative gradient means potential must decrease in the opposite direction of increase. So the fastest decreasing direction means the minus gradient. Okay, let us compute the minus gradient of potential energy is a force. We could integrate to find the solution, but you remember, you have never derived any integral in your whole life at all. What you have done is a fake. Why? Because you just carbon copied what you have done with the take the derivative. Just the inverse operation of derivative is the integral. So usually taking the derivative is much, much easier than taking the integral. So I would rather find the opposite way to find the potential energy. I could integrate the force, but I don't like it. I do this better. You can follow. First, what is the unit vector? Unit radial vector is a position vector divided by its own magnitude. Okay, position vector, we have a 3 dimension, so the sum of x coordinate, y coordinate, and z coordinate, divided by the magnitude, that is r. What I'm doing is just to simplify this expression. Simplify this expression. I would like to make an educated guess to find a function that satisfies minus gradient of this function is this. If I could find some u, then I have found the solution. First, we make a trick. We have a substitution. A capital X is this dirty thing. X1 squared, Y1 squared, X squared, Y squared, Z squared. Why don't we take the partial derivative with respect to x1, then it becomes a 2x1. We will make use of chain rule. Why don't we take the derivative? Oh, it's a trivial derivative. And after substitution, it is just 1 over 2r. All right, we are ready to find a final solution. R's derivative with respect to x1 is just like what we have done on the previous page. That is, this one is 2x1, 2x1, and this one is 1 over 2 square root x, and that 2 square root x is 2r, so 2 cancels x1 over r. Why don't we change this power from 1 to n? The next step is trivial. I again make use of chain rule. First, take the derivative with respect to r and take the derivative of r with respect to x1. Chain rule. This one, high school students can solve this. This n times r to the n minus 1. Because r is in the denominator, it changes the power n minus 2. The final answer is I can put this one in the denominator and flip the sign. So n times x1 divided by r to the 2 minus n power. Now I would like to find a way this is the same as the force. And the force, this force. The reason why I have put this negative sign, you will find soon. I just copy this one in here. I'd like to identify this one is the same as this. Then, what is the solution? If n equals minus 1, they are identical to each other. Using this result, I can simply write that because 2 minus 1 equals 3, using this one, r to the n, when n equals minus 1, that is 1 over r, what I have done is 1 over r's the derivative with respect to x1. That was this, right? So x1 derivative is x1 minus x1 divided by r cubed. If I replace x1 with x2, everything is the same except that x1 is replaced with x2. In a similar manner, x3 derivative must be this. Finally, what's that? If I multiply e1 hat, add them up all together, what I find is the gradient. Gradient of 1 over r is minus this one. What's that? This is x position vector divided by r cubed. But by definition, unit radial vector is this one divided by r. So I remove a single power in the denominator and replace x vector in the numerator with the unit radial vector. As a result, we have gradient 1 over r is negative of inverse square. I multiply minus both sides, then minus gradient of 1 over r is this. Finally, because minus gradient of potential energy should be the force, and I have nothing but the force here. If I multiply this expression by k, this is a force. Therefore, this guy, k over r, is proved to be the potential energy of the inverse scale law.